Hello everyone, my name is Alexander Krall, and I am here to present the project Gradient Mechanism to Preserve Differential Privacy and Deter Against Model Inversion Attacks in Healthcare Analytics. Advances in sensor technology are swiftly transforming healthcare into a data-rich environment through the Internet of Things paradigm. This newfound data availability has been leveraged by pioneers in the field. IoT sensing can be utilized for the real-time analysis of electrocardiogram signals for the detection of disease patterns. Nonetheless, the scale of this data transmission offers increased opportunities for data breaches. Such data breaches disrupt operations and destroy patient trust, costing institutions billions in revenue. Machine learning models utilized in analytics can be inverted and exploited. Some disturbing headlines indicate that standard anonymization is not sufficient to uphold privacy. Therefore, the research objective in the scope of healthcare is to be able to utilize analytics while mitigating the risk of exploitation by malicious agents. Prior to proceeding, some preliminary information must be established. For a particular database, we assume that the input is normalized to the L1 norm. Additionally, we assume that we are dealing with binary output and seek to release the parameters of a fitted logistic regression model. Differential privacy is a mathematical notion of privacy that can be employed to reduce the risk of discerning an individual's participation, or lack thereof, in a dataset. For a privacy budget epsilon, a function is said to be epsilon differentially private if it adheres to the theorem on screen. Essentially, differential privacy defines the allowable difference in distributions derived from two databases after running a particular algorithm. Applying the Laplace mechanism is one strategy to achieve differential privacy and involves injecting noise from a Laplace distribution into a function f. The degree of noise depends on a parameter delta, called the global sensitivity, which defines the maximum possible change in f should database D' be utilized as input in lieu of D. The mathematic definition of the global sensitivity can be seen on screen. Training a logistic regression model can be performed through empirical risk minimization. This family of models chooses a vector omega that minimizes the regularized empirical loss function. Utilizing a private ERM scheme entails strategically injecting Laplace noise at various stages of the machine learning process. Noise can be injected directly into the output parameters, into the objective function, or into the objective function's gradient. Within this investigation, we choose the lattermost approach with special accommodations for fast convergence. The flowchart on screen portrays the proposed gradient perturbation algorithm to achieve private ERM. The algorithm begins by accepting some input pertinent to the desired model. This includes the privacy budget epsilon, the regularization parameter lambda, the initial learning rate eta naught, the maximum epochs kappa, and the batch size b. Next, the model is initialized by determining initial values for the model omega. An iteration and epoch counter are also set to 1. A special parameter tau naught is also calculated, which is utilized in the automatic updates of the learning rate for fast convergence. The algorithm then proceeds to loop through the epochs and the batches of data. For each iteration of the method, the learning rate is first updated. Next, the global sensitivity is determined. A Laplace noise vector is drawn and then scaled by 1 over the batch size. This scaled noise vector is injected into the gradient of the objective function. Omega is then updated followed by incrementing the iteration counter. This process proceeds until a noisy model, omega bar, is received as output. Machine learning models are built from training data, which includes both sensitive and non-sensitive attributes. A model inversion attack leverages the derived model and known non-sensitive information about a target individual to infer information about a sensitive attribute. In this investigation, the adversary is assumed to have access to the released logistic regression model, as well as the patient's probability of mortality and complete non-sensitive information. The regression task at hand is to predict for a patient's mortality in the intensive care unit. The dataset has 45 input variables with 6,892 individuals. Thus, we are dealing with high-dimensional data. The response variable is a binary indicator which indicates a patient's mortality outcome. A baseline model is utilized to determine a patient's probability of mortality. For the sake of realism, the attacker's estimate of mortality risk is obtained by injecting some Gaussian noise into the baseline values of logit p. The privacy parameter epsilon is varied to determine the relationship between model performance and the inversion accuracy. The inversion accuracy is determined by calculating the coefficient of determination of the attack estimate. As one can see, the inversion accuracy decays at a faster rate than the model accuracy when epsilon decreases below 10 to the negative third. It should be noted that this decay is rather steep since the attack accuracy drops to 0 as epsilon approaches 10 to the negative fourth. At epsilon equals 10 to the negative fourth, the model accuracy only decays by around 5%, thus the majority of the model's utility is kept intact. The developed gradient perturbation technique is capable of reducing the risk of model inversion while preserving the performance of the logistic regression model. Nonetheless, given the steep descent of the attack accuracy, it may be difficult to determine an appropriate value for epsilon without needlessly degrading the model. Therefore, future work will entail developing a Mosaic gradient method that perturbs the gradient of sensitive attributes more intensely than the gradient of non-sensitive attributes. We would like to thank the Applied Research Lab and the National Science Foundation for supporting this work. Thank you.